Hello, and welcome to Lecture 4 of Phys 1104. In this course, and the next course, and a lot of your other courses, you're going to work a lot with vectors. So in this lecture, we're going to have a first look at vectors. If you want to know a lot more about vectors, I highly recommend a set of videos on a channel called 3 Blue 1 Brown called The Essence of Linear Algebra. I'll provide a link to that. Vectors have a very precise and somewhat abstract mathematical definition, but that doesn't really matter to us. For our purposes, a vector is a quantity that has both magnitude and direction, in contrast to a scalar, which has no direction, only magnitude. It's useful to be as concrete as possible, and a more concrete object that also has magnitude and direction is an arrow. So you can always think of a vector as just being an arrow. So here are two vectors. I've named them A and B. Note, the big, thick arrows are the vectors themselves. The little arrows over top of the A and B are not vectors. They're vector symbols. They're just drawn there to show you, or the reader, that A and B are representing quantities that are vectors. And we always draw them pointing to the right, no matter which way the vector itself points. It's just a symbol. So if I say there are two quantities Q and R, and I've told you nothing about what these are, you have no idea about what they're representing, except just from the way I've written them, you know that Q is a scalar, but R is a vector, because I've drawn a vector symbol on it. We're going to meet lots of quantities that are both scalars and vectors, and you've probably met most of them in other courses before. Speed, distance, mass or inertia, energy, and temperature are all scalars. On the other hand, velocity, displacement, force, momentum, and electric field are all examples of vectors. Let's go back to thinking about this vector A that I drew. I've drawn it with some length, and we can think of that as representing its size. But note, A might not be a vector that's measured in units of length. It could be a velocity, or a force, or an electric field, so it could have other units. Nonetheless, it has some size, which we call its magnitude, in whatever units that would be measured. And we represent the magnitude of A by simply writing A without the vector symbol on it. Or alternatively, we write the A vector inside absolute values. So these are two ways of writing the magnitude of A. Compare the two vectors that I drew earlier, A and B. I hope it's visually obvious that A and B are not equal. Similarly, A and this new vector C are not equal. But if you take a ruler and check on your screen, you'll notice that I've been very careful to make C the same length as A. It doesn't matter. C is still not equal to A because they point in different directions. On the other hand, this vector D is equal to A. They have the same magnitude and they point in the same direction. The fact that I've drawn them in different places doesn't matter. You can move a vector around as long as you don't change which way it's pointing or its size, and the vector doesn't change. Even if I identify some axes, so I've now defined an origin, it still doesn't matter where I draw a vector. All that matters is how long it is and which way it points. And so in particular, if I move this vector B up here, so now it just happens to be pointing to the same location as the vector A, it's still not the same as the vector A. It points in a different direction and it has a different length. One of the main reasons we have to pay attention to whether a quantity that we're using is a vector quantity or a scalar quantity is that calculations with these quantities work differently, whether they're vectors or scalars. So let's look at how addition and subtraction work for vectors, which is not quite the same as addition and subtraction for scalars. And we're going to use some key facts that we already know. Vectors have magnitude and they have direction, and that means they are representable as arrows. And I mean that in a mathematical sense. They really are just like arrows. Anything you can do with arrows is a valid thing to do with vectors. So let's look at addition of vectors using the representation of them as arrows. So here are two arbitrary vectors. What does it mean to add them? Well, what we mean by addition of vectors is that we take one and put its tail on the head of the other. And then the sum is the result of starting at the tail of one and following them both to the end of the second one. A straight arrow pointing from where you started to where you finished is the sum of these two vectors a and b. What does that mean? In what sense is this addition? Well, think of it this way. If you started here and walked along this vector and then along this vector, it has had exactly the same effect on you as if you had started here and walked this vector instead. And so we say this vector is the result of doing these two, of adding them together. What other mathematical operations can we do with vectors? Well, we will eventually see two different ways of multiplying vectors together, but we don't need that yet. But what we will need is how to multiply a vector by a scalar. And it's easy enough to see how it works. Suppose we take b and add it to itself. Then we get 2b. But that's just the same as multiplying b, the vector b, by the scalar 2. And so we see all that happens when we multiply a vector by a scalar is that we change its length. We rescale it. If you multiply it by a negative number, it flips it end to end. Knowing how to multiply a vector by -1 is what we need to understand vector subtraction. Note that a minus b would be the same thing as a plus negative b. And so this tells us how to do a vector subtraction. Start with our vectors a and b. Let's flip b around so that we have negative b, and then add that to a, and what we now have is a minus b. We're going to learn ways of doing this all algebraically by manipulating numbers in equations. But it's important to realize that while that's convenient and powerful, the real meaning of vector addition and subtraction and multiplying by a scalar is given by pictures like this, and so you should never forget these pictures. Manipulating vectors this way by drawing pictures is often called graphical vector addition and subtraction, as opposed to algebraic vector addition and subtraction. So when I say graphical vector manipulation, I don't mean we're drawing a graph. The word graphical just means with pictures. How do we know that a number is negative, or for that matter, positive? Well, the answer is that we need to know where it lives on the number line. If it lives to the left of the 0 on the number line, then it's negative, and if it lives to the right of the 0, then it's positive. And so I can tell you there's some number a, and without telling you exactly what it is, if I just point you to where it is on the number line, you can now see that this a is negative. Okay, so now I'm going to ask a similar question. Is this aardvark positive or negative? Well, hopefully you're saying, that's ridiculous, Jeff. Aardvarks don't live on number lines, they live on brushlands and savannas of Africa. And so we have no way of deciding whether an aardvark is positive or negative, and so it's a totally meaningless question. Well, so, is this vector positive or negative? Well, I hope you see that this is exactly as ridiculous as the question about the aardvark. The vector doesn't live on a number line because it isn't a number, it's an arrow. And so it's totally meaningless to ask whether it's positive or negative, and similarly, it's totally meaningless to describe a vector as either positive or negative. Let's check your understanding. So, if you're following along in Moodle, Moodle will now ask you this question before going on to the next part of this video. If you're not in my course or you're otherwise not on Moodle, I still think you should decide what the correct answer is here before you go on to the next part of the video. So, given vectors a and b that I've drawn over here, which of these is the best representation of 3a minus 2b?